Hello, and welcome to our presentation. Thank you very much for joining us. If you have any questions during the presentation, you can press the Q&A button at the bottom of your screen and submit the questions. Thank you. Okay, today we're going to go over how does imbalance affect mechanical seal, bearings, ring, sleeve, and motor life. My name is John Kozel, president of Sims Pump. Thank you. Okay, the question is, how long would a motor last without an impeller? Well, the answer is indefinitely. It lasts indefinitely because it doesn't have a heavy, unbalanced impeller at the end of the shaft. If it had an impeller which was lightweight and didn't go into an imbalance, mechanically or hydraulically, the motor would last indefinitely. And that is the goal we're going to talk about today, how to achieve that. Factors affecting shaft deflection. Okay, here this slide shows two impellers. One is a bronze, sorry about that. One is a bronze impeller. The other one is a Simsite carbon fiber impeller. Now the bronze impeller weighs 120 pounds. It's the same impeller. The Simsite carbon fiber impeller weighs only 20 pounds. It's a huge difference. You can see the shaft deflection, and this shaft deflection causes premature wear on the mechanical seal faces, the bearings, the rings, and of course the motor, sleeves, other internals. It doesn't matter whether the pump is horizontal or vertical. This weight and inherent mechanical and hydraulic imbalance of cast metallic impellers causes this, what I call the pendulum effect. Like a pendulum on a clock, the impeller acts like a weight at the end of the shaft, and the shaft starts to wobble or deflect. Any type of corrosion, erosion, cavitation increases this pendulum effect. The motor bearings can't hold the stresses, and you have premature failure of your mechanical seals, sleeves, motor bearings, etc. Now, the failure is proportional to the weight and the speed and the amplitude of the mechanical imbalance, as well as the radial loading on the shaft as a result of hydraulic imbalance, which we will get into later, a little bit later. So the heavier the weight, the worse it is. The greater the imbalance, the worse it is. Here I have a little video of a metallic impeller, and you can see this wobble that takes place, and you can see also the effect on the mechanical seal on that shot. Now, in this slide here, I showed this because it shows the shaft deflection, but I want to show the number of shaft deflections that occur as the vanes pass the cut water or the exit port of the pump. A lot of people don't think about this, but if the impeller has 5 vanes and is turning at 1,750 RPM, in 1 week, there's 88,200,000 deflections. It's huge. In a year, it's 4.5 billion. Now, if it's turning at 3,600 RPM, in 1 week, you have 181 million deflections. Those deflections are causing this premature wear of the seals, the bearings, rings, and in some cases, it breaks the shaft. Many times customers say to me, oh, I don't have an impeller problem, I have a mechanical seal problem, or I have a bearing problem. No, they don't have a mechanical seal or bearing problem. What they have is a hydraulics problem. This imbalance is causing the premature wear of the seals and the bearings. So when customers think that they're getting a good deal by buying a cheap bootleg impeller, one from China, India, or some other place, they don't think about all the imperfections on it. They don't think that the vane passageways and channelways can be different. And if they are, that causes hydraulic imbalance, which is a huge problem. We'll get into that just a little later. This slide here shows a Simsite carbon fiber impeller. Go back here, try it again. So technical difficulty. There we go. You can see how smooth it is as it's turning. No deflection on the shaft or the mechanical seal. And it is 85% less weight and perfectly balanced. It's huge. Perfectly balanced mechanically as well as hydraulically. Now, there are three major forms of imbalance. First one, mechanical, which we're all very familiar with. And with pumps, it's dynamic imbalance. Then there's hydraulic imbalance. Now, this hydraulic imbalance is just as important, just as damaging as mechanical imbalance. If the exit ports of vanes are not equally spaced, you have unequal forces, and that causes greater deflection as each vane passes. It causes it to deflect. This is a huge problem. Same thing with radial thrust imbalance. We'll talk about this a little bit later. That's why it's so important to operate at the best efficiency point. At the best efficiency point, your radial forces are almost nothing. But if you go back on the curve, around on the curve, they become tremendous, and they cause tremendous shaft deflection. And we'll discuss that a little bit later. Now, let's talk about the different forms of imbalance. Corrosion, we're all familiar with that. The greater corrosion, not only do you have loss of efficiency, but you have this tremendous imbalance and loss of performance. Imbalance from cavitation. This is an operational problem, but if it's not operating at the best efficiency point, it cavitates. You have different forms of cavitation, but all cavitation destroys the impeller, and it leads to imbalance and tremendous shaft movement and deflection, vibration. Imbalance from recirculation cavitation. Again, performance not correct. You're operating out on a curve. You have this recirculation cavitation, back on the curve or out on the curve. It tears up any material known to mankind. The only solution is to redesign the impeller. That's the only thing that solves this type of problem. Imbalance from erosion. Again, it causes imbalance, and quickly you have failures of your seals, rings, bearings. Imbalance from clogging is also very important. A lot of your wastewater pumps have huge problems with clogging. This clogging causes the imbalance, and that sets up premature pump failure. Then there's unbalanced design. Okay, a lot of your wastewater impellers suffer from this imbalanced design. They're inherently unbalanced from the beginning, okay? And this leads to, along with the corrosion, it leads to premature pump failure. And think about these big, heavy impellers at the end of the shaft. Again, the farther away you are from the bearing support and the heavier the impeller, the worse is the deflection. So your shaft is deflecting even more. It just accelerates the problem. Now let's talk about this not operating at the best efficiency point. The pump is designed to operate, you want the pump to operate at the best efficiency point. But that best efficiency point, you want to be your operating point where the pump is operating. If it's not, if it's operating back on the curve or out on the curve, you can see this radial thrust curve here increases as you go out away from BEP, and it increases substantially as you go towards shutoff. This causes tremendous pressure on the shaft, and it causes premature pump failure. And in many cases, this is where we see a lot of the shafts being broken. Okay, it's a shear break. And it happens right behind the impeller. I put this curve up here so you can take a look at where you want your pump to operate. You want your pump to operate in the safe operating zone. This safe operating zone is plus or minus 5% from the best efficiency point. In this case, it's 5,400 gallons per minute. This particular pump was operating at 4,000 gallons per minute, 74% of BEP. And at that point, they couldn't even keep the pump operating. It was vibrating so badly. Now the same thing happens if you go out and you go out on the curb and run at 6,000 RPM, 6,000 gallons per minute, I'm sorry. At 6,000 gallons per minute, you're gonna have the same problem. You're gonna have tremendous vibration and cavitation. And these are what we call the danger zones. If you're not within 5% of the best efficiency point, you are operating in a danger zone. Now, how does that relate? Well, when you buy a production pump, you're not buying a custom engineered pump, you're buying a production pump, and it's not, the best efficiency point is not where your operating system is, where your operating point is, then you're going to have these problems unless you upgrade to a SimSite impeller and redesign. So let's continue down the path here. So what is the solution? The solution is to use a lightweight, completely machined impeller, such as a SimSite carbon fiber impeller. It's because it's machined from a center position, there is no imbalance. When you're machining, we can make sure that the vane passages are all equally spaced. That way you don't have this hydraulic imbalance and you don't have mechanical imbalance. The mechanical balance is eliminated by machining from one center position. For example, the wheels on your car, if we machined them, if they were machined from one center position from a solid block, you would never have to balance your wheels again. It's huge. Okay, and in this case, we're 85% less weight. The other point is that we're designing the pump to operate at the best efficiency point. So if your specific requirement is 1,257 gallons per minute at 103 feet ahead at 1,750 RPM, we're designing that point to be the best efficiency point. And that's the advantage of machining. You can machine it to any point. You can design the impeller to make the operating point the best efficiency point. And that is so important because it eliminates all these balance problems, hydraulic as well as mechanical. And the SimSite impeller, you eliminate corrosion, cavitation, erosion, electrolysis, and performance deterioration. People forget about performance deterioration. If you put a metallic impeller in service in any type of corrosive service and look at the performance 6 months later, a year later, your performance has deteriorated substantially. That doesn't happen with the SimSite carbon fiber structural composite impeller. That all those problems are eliminated. Here's a slide of a SimSite impeller operating. You can see how smooth everything is. It doesn't matter whether it's horizontal, vertical, the pendulum effect is totally eliminated. All balance problems are solved. Thank you very much.
John, do you want to take questions?
Sure. Let me see if I can answer some questions here. Yes, the Hydraulic Institute says that it's plus or minus 10%. That's correct. The question is, I thought the Hydraulic Institute defines it as being plus or minus wider range than 5%. It's true, but 10% is really off quite a bit. When you're 10% off, you start to have problems, and you can start to have cavitation problems. You can start to have imbalance problems. You can have radial loading problems, and that's not what you want. Okay, you want it to be plus as close to the point as you can get. So it's true that they picked a random point, but you want to be as close as you can be. And I think plus or minus 5% actually is pretty liberal. So, but this is from our own experience. Sims has been in business 101 years. We've been dealing with pumps entire time. So this is our professional position. Now the second question is tolerance of unbalanced impellers. Let me know the tolerance of unbalanced impellers. Well, again, you want to not deal with tolerances. You want to deal with a machined impeller such as a Simsite impeller, which is machined from a center position, so you don't have to deal with the tolerance. Now, the tolerance is you're talking about is mechanical. Again, mechanical is just one type of imbalance. It's only one part. You have hydraulic imbalance, which is even more important than the mechanical imbalance. So you want to be on a hydraulic point of view, if you're looking at hydraulic and vane passages and everything, you want to be within a few thousandths. Each vane passage has to be within 1 or 2 thousandths of each other. Okay. Now the next question is, how do you size for VFD applications that have a wide flow variations? Oh, very good question. Well, our experience has shown that with variable frequency drives, VFDs, that with only a few exceptions, mostly they're operating at a certain point. So there's a primary position. We would design the pump or impeller for that primary performance. And then the VFD would change the speed depending on the requirements that are set with the variable frequency drive or whatever parameters are set. So we would design specifically for the general range. And that's really important because a lot of people think that you can take a variable frequency drive and you can run it down as low as you want. No, you're going to have problems with your seals, bearings, everything. And you're taking an impeller which is designed for a different performance and you're changing it. So it has tremendous effects. So the best is to buy upgrade to a Simsite impeller which is designed for the general range where you're operating. And you don't want the variable frequency drive, if you can avoid it, to swing too much. You want it, it's okay to swing a little bit, but not too much. Okay, next question. You have ASTM 1511 for mechanical seals. Okay, well, we are making our mechanical seals out of the Simsite structural carbon fiber composite. We also use other mechanical seals, such as Cheston mechanical seals. But if we're making our own mechanical seals, then we're using Simsite structural composite. So it has different standards. Every one of our seals are tested in-house. Every seal is tested, and it's tested. Performance tested as well. So it's dynamically tested, and I'm not sure about this particular ASTM. I'll have to take a look at it, but we can discuss it later. I'll take a look at it and get back to you with that answer. But ours are a little bit different. Okay. Next question. How do you machine the impeller vanes? Oh, very good question. What we do is we put the solid block of the patented Simsite structural composite up on a 5-axis machining center, 5 to 8-axis machining centers, and we machine from center position. So the impeller vanes are designed first in the CAD and then in the CAM system, and they're designed specifically for the operating point. And then we machine everything on the 5-axis machining centers. The cutters come in from all sides, and it's made in one solid piece. Okay, next question. If we want to solve a cavitation problem, changing the impeller for Simsite will be enough. Yes, that's true. What we would like to see here is I'd like to see photos of the cavitated impeller, or you can send us the damaged cavitated impeller, because each type of cavitation has a form and it has a telltale signs. So by looking at the damage, we can determine what type of cavitation it is. Then we need to know where the pump was operating. So I'll need the suction and discharge pressure readings where you're operating that pump. We'll redesign to eliminate the cavitation. That by redesigning, that's the only way to solve cavitation. Some people might tell you can go harder or softer on the materials. It's nonsense. It'd take anything out known to mankind. All right, doesn't matter how hard, how soft. You're only adding a little bit of time. Maybe you get a couple weeks different, but it's still going to fail the pellet. So what we do is we're eliminating cavitation through redesign. It's the only way. Okay, that was a great question, really. Okay, another line with ASTM. Okay, I'll get back to you on these ASTMs. All right, we are using our own composite, which we manufacture. So our ASTMs are a little bit different. Okay, than they would be for a metallic bumper and pellet. Next question: are there any limitations for certain fluids, such fluids that may weaken or damage the Sims impeller? Yes, it's a good question. Uh, the limitations are limited to the resin system, which is a hybrid phenolic epoxy. So just like with 316 stainless steel, it has a range of chemicals that it's good with, and some that it's not good with. The range is larger with Simzite, of course, but if it's not compatible with the epoxy phenolic resin system, then we would stay away from that. Have to use another resin system for that particular fluid. But with salt water, there's absolutely no corrosion. With sewage, wastewater, absolutely no corrosion. Chlorine, bromine, it's good with hydrochloric acid, sulfuric acid. It's good with a lot of chemicals. But if it's a chemical or a cocktail that we don't know, well, we have coupons. We send the coupons out, and you do an immersion test, because the carbon fibers are pretty much impervious to everything. But it's the resin system we have to be careful with. And also we might have a limitation on temperature. So we stay away from applications 400 degrees Fahrenheit and above. Okay, the next question is, do you have a file to fill? I'm not sure what you mean by file. Not sure. You have to get back to you. I'm not sure what you mean by that question. Okay. Do your pump controllers have any IP ratings? Yes, if we're using a controller, we are using fully rated controllers. Yes, that's correct. Oh, I mean the format to fill. Okay. We have a standard format which you can fill out for a pump application. It asks you all the parameters that we need, and based on that, we can quote any type of pump, any type of centrifugal pump you're looking for. Okay. In case of impeller failure, how have the impellers failed? What should be expected? Well, we don't have any failures that I can really think of. If there is I've been here 40 years, and I don't know of any failures that we've had. But okay, we have had problems where the impeller wasn't sized properly. So if we had an incorrect bore diameter, or we were given incorrect shaft diameter, someone measured up a unit incorrectly, you could have a problem, and we'd have to re-engineer and correct the problem. But those were dimensional type problems. It's just like with a computer. You put the correct information in, you get the correct information out. Put the wrong information in, so we have to have the correct information from the start. That's the only type of failure we've experienced when we've been given incorrect information. Oh, well, thank you. Appreciate it. Thank you for all the questions. They were all good questions. Thank you very much. Appreciate it.